Autocomplete predicts the next piece of code. It can finish a function call, suggest a parameter, or fill in a familiar pattern. That is useful, but it is still a suggestion engine. Agent-based coding changes the unit of work. Instead of asking for one completion, you give the system a task. Inspect this project, make the change, run the tests, read the failure, and revise the code until the result works. The important shift is not that the model writes code. Models have done that for years. The shift is that the model is connected to tools. It can read files, edit files, execute commands, and use the output of those commands as feedback. That is what makes agentic coding different from autocomplete. An agent-based coding system is a model wrapped in a runtime that lets it act on a codebase. A chat model can explain how to add authentication to a fast API app. It can generate a sample route or outline the migration. But the developer still has to copy the code, place it in the right file, install dependencies, run the tests, fix the import error, and check the endpoint. An agent workflow moves more of that loop into the system. The agent can inspect the existing app, create an auth module, update requirements, run the test suite, observe the failure, and make a follow-up edit. The model is still not an independent engineer. It needs constraints, tests, permissions, and review. But it is no longer only producing text. It is operating inside a controlled development loop. That loop is the core idea. Most coding agents follow the same basic cycle. Think, act, observe. In the think step, the model receives the task and decides what information it needs. It may inspect the directory tree, read a configuration file, or search for an existing pattern before changing anything. In the act step, the model emits a tool call. That might be read, file, edit, file, search, files, bash, or a git operation. The runtime validates the call and executes it. In the observe step, the system returns the result. The model sees the file contents, test output, compiler error, or command failure, then decides the next action. A practical agent needs 5 pieces around the model: a system prompt that defines the rules, context management, a parser for structured output, a tool executor, and error recovery. Without those pieces, the model is just a chatbot with a longer prompt. The tools fall along a spectrum from cloud-first to local-first. Claude Code is the strongest hosted agent option right now. It has excellent model quality and a polished agent experience, but it depends on Anthropic's API. Your code is sent to a remote service, and usage is billed by tokens. OpenAI's Codex CLI is open source and uses Docker sandboxing, but it is still built around cloud model access. Aider, the open source coding agent, is one of the most mature options. It supports many model backends, manages repository context with a repo map, and integrates cleanly with Git. For many developers, it is the simplest place to start. Hermes Agent is designed around local and open-weight models, such as QWen3 Coder. The architecture assumes the model can run on your own hardware, and that tools, prompts, and routing should be configurable. OpenHands provides a web UI with Docker isolation and browser agent features. SWE-agent is commonly used in academic benchmark work, especially around SWE-bench. OpenCode is a lightweight multi-backend option with local inference support. The practical choice depends on what you care about most: model capability, privacy, cost, latency, or control over the runtime. The answer depends on the task. For complex architecture work, ambiguous debugging, or large refactors, the best cloud models still have a clear advantage. They reason better, follow long plans more reliably, and recover from mistakes more often. Local models have improved quickly though. A year or two ago, they were not reliable enough for serious coding agent workflows. They struggled with function calls, lost track of context, and scored poorly on SWE bench. Recent coding models changed that picture. Qwen3 Coder 32 billion parameter can run locally at practical speeds on high-end consumer hardware. It supports long context, follows agent prompts well, and can emit structured tool calls with enough consistency to be useful. That does not make it equivalent to Claude. The gap is still real, but local models now work for a large class of routine tasks: boilerplate, focused bug fixes, small feature changes, test generation, documentation updates, and mechanical refactors. The enabling factors are straightforward: better function calling training, longer context windows, stronger instruction tuning, benchmark-driven coding improvements, and quantization. A 32 billion parameter coding model can fit in roughly 18 gigabytes of VRAM at 4-bit precision. That makes local coding agents practical, not theoretical. Tool use is the mechanism that turns a language model into a coding agent. Without tools, the model can only produce text. With tools, it can request an action in a structured format. For example, edit this file, find this string, replace it with this new string. The runtime receives that request, validates it against a schema, performs the operation, and sends the result back to the model. If the edit failed, the model sees the error. If the tests failed, the model sees the traceback. If the search found the wrong file, the model can adjust its plan. The common toolset is small: read files, edit files, create files, run shell commands, search the repository, inspect diffs, and commit changes. Some systems add web search, browser control, or explicit user clarification tools. Local models used to fail often at this layer. They would produce invalid JSON, invent parameter names, or wrap tool calls in Markdown. Newer coding models are trained more directly for structured output, and grammar-constrained decoding can enforce valid formats. That reliability is what makes the loop usable. Local and cloud agents are not interchangeable. They solve different constraints. Local systems are strongest when privacy, cost control, offline access, and customization matter. The code stays on your machine. You can change the prompt, swap the model, add tools, or run against a private repository without sending context to an external provider. Cloud systems are strongest when capability and speed matter. The best hosted models are still better at difficult reasoning. They usually produce tokens faster, handle very large context windows more comfortably, and have more reliable tool use behavior. A hybrid workflow is often the most practical. Use a cloud model for hard architecture questions, unclear failures, or multi-step debugging where model quality dominates. Use a local model for routine implementation work, repetitive edits, tests, documentation, and tasks with clear acceptance criteria. The hardware flaw is also real. A 24 GB GPU, such as an RTX 3090 or 4090, is a comfortable target for 32 billion parameter class quantized models. Smaller cards can run smaller coding models, but the reliability and context trade-offs become more visible. The decision is not local versus cloud forever. It is which tool fits the task in front of you. Local coding agents still have clear limits. They can struggle with large, multi-file refactors, especially when the change depends on implicit project knowledge. They can be slow during planning. A local model running at 5 to 20 tokens per second may pause for 30 seconds or more before acting. Tool reliability is also not perfect. If the model emits a malformed call or chooses the wrong parameter, the runtime needs to catch the mistake and recover. Without good guardrails, an agent can repeat the same failed edit or chase an error in the wrong direction. Setup is another barrier. Running Ollama or llama.cpp, choosing a quantization, configuring endpoints, and connecting an agent runtime still takes more work than using a hosted assistant. The direction is clear though. Local coding models are getting better at long context, tool use, and instruction following. Speculative decoding can reduce latency, On-device accelerators will make local inference more practical on laptops. The result is likely not a single replacement for human developers. It is a tighter development loop where models handle more of the mechanical work, and humans spend more time setting direction, reviewing changes, and deciding what should be built. Coding agents are the move from code suggestions to tool-using systems. The model plans, calls tools, observes results, and iterates. Local models now make that loop practical for a meaningful set of development tasks, especially when privacy, cost, or control matters. They are not a full replacement for cloud models, and they are not a replacement for engineering judgment, but they are becoming useful enough to fit into real workflows. For developers running local LLM infrastructure, this is one of the most important applications to understand. If you want to try this locally, start with Aider or a local first agent runtime, connect it to a coding model like QN3 Coder, and give it a small, testable task. Keep the scope narrow, review the diff, run the tests. Treat the agent as part of the development loop, not as a substitute for it. Subscribe for more practical work on local AI development.